こんにちは。私はアメリカから来ました。カールサイズのエルミンソビジャラガゴメスです。私は日本語を話しません。では、どうやって話していると思いますか？私はカンニングしてます。私は実践に要した読み仮名付きのスピーチを読んでいます。日本語に来られたことを大変嬉しいと思います。3次元 X 線検査による電池の良化についてお話ししたいと思います。これから私が日本語でできることの限界です。ありがとうございます。すみませんが、これから英語に切り替えます。Okay, that's better. Now I can speak English. Today, rechargeable batteries play an essential role in the world we live in, to the point that almost every major automaker has announced a transition from combustion engine cars to electric vehicles in the next 10 to 30 years. One of the biggest challenges facing electric cars, as we might have heard of, is the batteries. They face different challenges in terms of manufacturability, performance, load capacity, durability, and safety concerns, and pose other challenges in terms of quality inspection and failure analysis. From the several techniques that exist to inspect batteries, there are several of them, including light microscopy, electron microscopy, and X-ray microscopy. And the graph that you see on the screen plots how much you can penetrate inside of the sample and the wavelength, basically the type of features that you can see inside of the sample. And though there are techniques like electron microscopy that produce high-resolution images, X-ray microscopy has the main advantage of being non-destructive. So you can see inside of the battery without opening the battery itself or destroying it. Or unless you want to do very advanced studies and you need very tiny, small samples to do very, very high resolution down to nanometer scale. The other plot that you see in my left, that would be your right, is the type of techniques that you can use and the type of features in a scale. So you see a scale there that tells you the type of features that you see in lithium-ion batteries. And from X-ray imaging, there are several techniques. The classical approach is to use an X-ray source, as you can see in, let me see, as you can see in the image over here. And then you have a flat panel and a rotational stage to put the sample. The sample is going to rotate while the detector collects projections, and then you use those to create a 3D image reconstruction. Those systems are based on something that is called geometrical magnification, and it has one limitation in terms of resolution, that is you have to put the sample very close to the X-ray source to get the highest magnification, and that means that the size of the sample is also somewhat limited. There are some more advanced techniques that are, we call it X-ray microscopy, that equip the system with a set of lenses that add optical magnification. So what you have is a combination of geometrical magnification and optical magnification to gain extra resolution, and now you don't necessarily need to put the sample so close to the X-ray source, because we have something that is called resolution at a distance. You basically switch those lenses to get the right magnification. There is a trade-off in field of view. The field of view decreases, but the idea is basically the same that you have in a light microscope, that you can switch between different lenses, and that's why we call that X-ray microscopes. The typical workflow is shown here. basically an operator is going to set up the main parameters to scan the sample based on size and composition of the sample. Then we start collecting projections, typical radiographs as you do in the medical imaging, and use those to use a reconstruction algorithm to create a 3D image. Once you have that 3D image, you can access to slides inside of the sample, virtual slides, without cutting the sample physically. You are cutting it with a software to see what is inside and see all kind of inspection defects or evolution over time. This is a typical example of an 18650 lithium-ion battery, and you see a couple of images there. One that was acquired with a low resolution scan is in the background, and you can see that the features are somewhat limited, but then when we use the 4X lens, you can magnify and now see at higher resolution more details, and you can see some of the particle inclusions and some features that is going to generate kind of a crack here between the different layers. This other example is a 21700 lithium-ion battery, and you will see here a video that shows how we scan different regions of interest. The battery, again, is intact. We haven't destroyed or select a good portion of the battery. We scan the full battery and then zoom in with the lenses to scan a smaller field of view and a higher resolution. And you see features there like particle inclusions. And at some point in this video, you're going to see that as we zoom in to scan a smaller field of view at a higher resolution, you'll see now the segmentation of a crack at some point. This is coming up in the video. I think it's the next one. Yeah. And right there. There you go. So the typical workflow is you basically try to get the largest field of view that you pull in the battery and see if you are interested in a particular region of interest, and start zooming in to scan at a higher resolution a smaller field of view down to 2 micrometer per voxel. And for those that are not familiar with this technology, voxel means a 3D pixel, basically, in a pixel in 3 dimensions. So it's a cube, basically, a cubical unit. And it's not just about collecting high resolution images. You can also see the level of contrast that you can get in some of the low density features inside of this battery. Oh, sorry, one more time back. And this example shows now how we can scan a battery that goes into a smartphone. And you can see all type of features. Not only you can image the full smartphone, but now target the small features in the battery to see any traces of degradation after several cycles of charging and discharging, to the point that you see some delamination over there. And again, here is a little bit of the workflow. You see the schematic setup of the battery inside of the system, and images collected with the flat panel, with the 0.4x, with the 4x, and all the way with the 4x lens, which you can see how the details of the image that you can get once you start zooming in are greater and greater. And because you have the 3-dimensional volume, then you can go inside virtually and make some type of videos to see what's happening across the full volume. And you saw passing by the traces of some voids or porosity inside of the sample and unpacking of those particles after degradation. And you can see traces of delamination and features at high resolution, as you can see here. When you increase the magnification all the way to the particle level, you can see the granularity. And again, this is acquired with X-ray. It's not an electron microscope image, so it's really great to get this 3-dimensional volume non-destructively or non-invasively. A typical workflow that some people do is they do aging studies. And as you can see here, we have a fresh battery and then a battery that was cycled 200 times. And you can notice that some of the silicon particles that are here disappear after 200 cycles. if we scan somewhere in between, you can see what is happening. The particle is being pushed away and consumed after cycling the battery. And this is really important to study what's the performance of the battery after several cycles of charging and discharging. It's not only to see what is happening inside, but also to study a little bit of the morphology. And you can see what happened. This is a metal anode battery, and you can see what happens after 80 cycles of charging and discharging. The anode deflects, and this can cause problems in the performance of the battery. So morphological studies can be done. Now, I have been talking about X-ray microscopy and X-ray computed tomography. X-ray microscopy, as is explained in the plot, is really great to study some of the small details inside of the battery, including materials from the electrodes. And now, if you want to scan larger batteries, there is a compromise. You probably won't be able to do with low energy X-rays, and you will have to raise the kV from 160 to maybe 220 and 450, but then the resolution is compromised. However, you still see some details that you might be interested in the large shape of the battery. So with X-ray computed tomography, you can even see the full battery pack. And here is some summary of the details that you can see with X-ray computed tomography, including particle inclusions or to scan the electronics and see some overhanging of these electrodes inside of those batteries. And if you want to know more, there is a reference there that you can consult. The time here is short, but it is published and it's open access. Now, this is about the technology. Nowadays, we hear a lot of artificial intelligence. So, in the second half of my talk, I'm going to explain what are we doing to adopt artificial intelligence technologies to X-ray microscopy. And we have a couple of ways we are doing it. So, the first thing is I'm going to explain how are we doing. We collect the radiographs and when use a deep learning algorithm to go to the reconstruction. And I want to clarify that because most people do deep learning after the reconstruction process. This is not happening there. This is happening before the reconstruction. And here is an example of a 21700, which to get a good quality image, you need over 3,000 projections. If you reduce the projections, then you start seeing some noise artifacts. This is the standard way of reconstruction. If you use deep learning now, you can use less projections and get the same 400 projections and get great quality image. So you speed up the scanning. Now, if you want to scan now all the way to small details, again, when you start putting the projection in the standard way of reconstructing, you see a lot of noise. If you use deep recon, then now deep learning algorithms, now you see much more clarity to the way that you can segment all of the components of this battery. And if you still want the best quality image and you don't care about time, you can get images like this, which give you much more clarity. And that's what deep learning algorithms bring to you. The second way we are doing it is there is a compromise between field of view and resolution. So you get great resolution, but the field of view is small. And a way to solve this is the classical approach that people will do is, okay, if they want high resolution, they will scan a small field of view and then maybe repeat that over several field of view to stitch the sample. But that proved too long. A better way to do it is now to use deep learning algorithms, scan a high resolution section of the sample, now a low resolution of the sample, and apply deep learning algorithms to recover the resolution of the details of the data. And here, how much time is left? 1 minute. There are a couple of examples here, and this is explained with a small field of view how you can expand to one of those pouch batteries that I just showed you. And another way to do it is one of those solid-state batteries where you can see here a large field of view, a high resolution in a small field of view, and high resolution. And you can use these deep learning algorithms. You can see the details to combine those two and expand the full high-resolution scan to the full field of view without taking a lot of scans. So you can see the difference, what is happening in the top of the battery, in the bottom of the battery, and recover the resolution for the details that you wanted to see in this battery. This is a little bit of a comparison of the three different methods: full field of view, low resolution, high resolution, and then deep learning algorithm, which is more or less similar to what you see in the middle. This is now a summary of those ways that we are using artificial intelligence. Remember, the first, to reduce the number of projections and reduce the scan time, because you can get great quality of data with less projection. The second one is scan a small field of view at high resolution and expand that to the full field of view, so you get a larger field of view with greater details. And this will summarize the presentation I wanted to bring to you today. Domo arigatou gozaimasu.
Now the talk is open for discussions. Any comments or questions? どうぞお願いします。マイクを使ってください。スタンドマイクがあるので、そちらまで出ていただいて。
Thank you very much. It's Igor from University of Oxford. It's a very interesting presentation. My question is about, is that possible to distinguish between carbon black and air, like where there's cracking? Because I think for CT scanning, normally that's one of the most challenging parts. Thank you very much.
Yes, so with normal CT scanning, it might be challenging. With X-ray microscopy, you might have a better look. From some of the images that you saw, we can see greater contrast, not only when you have high density materials, but also low density materials, and it's possible to see difference between air and some of those low features. If the density of the material is too close to something like air, then yes, I agree, it's going to be challenging, especially if you have high density materials, because you need to do a balance between the X-ray parameters. In that case, the best situation is to try to isolate those high density materials like metal encasing, and have a sample that has only low density materials, and you might be able to differentiate. But still, it might require some tweaking of the parameters.
Thank you very much.
You're welcome.
Please use mic.
Yeah, my question is, what kind of strong X-ray do we need for these techniques? Do we need synchrotron radiation X-ray or something?
No, we don't use synchrotron radiation. We use normal X-ray sources. But what we have leveraged from synchrotron technology is the detection system. So what you see when you saw the setup, and you saw those lenses, on top of those lenses, there are different scintillators. So each one of those lenses has a scintillator on top, and that scintillator has a different thickness that is target for different type of X-ray radiation and the resolution that you want. So you switch the lens, and the X-ray goes into that scintillator, and then after that, it goes through a set of lenses, normal lenses. So the scintillator converts X-rays into light. That light now passes through a set of lenses that get magnified before going into a CCD camera. And then now you have the image at a higher resolution that goes from the CCD to your computer screen.
Okay, thank you very much.
Okay, so time is over. Thank you for your presentation.
Thank you very much.